probably the hardest part about these problems is that it's not immediately obvious that you need to use trig at all. In this example, it tells us to find all the complex number solutions to x to the fifth minus 1 equals 0. And if we were solving this based on the way we've solved these problems before, we would have x to the fifth is equal to 1 by adding 1 to each side. And then to solve for x, we would take the fifth root of both sides, and the fifth root of 1 is just 1. Now, there's nothing wrong with that. That is one of our solutions. That is the only real solution. And remember that real numbers and complex numbers belong in the same group. Every number, whether real or imaginary or a combination of the two, is a complex number. So 1 is one of 5 complex solutions. But since I'm taking the fifth root of the number, there are really 5 solutions, and I need to find the other 4. So that's what we're going to be doing here. Sometimes they give you that in equation form, and you just need to recognize that that's what they're asking you to do. After that, and the fact that we're not going to have special angles in this problem, we're going to have to use the calculator. Everything else is just like the problems that we've worked before. Let's work through this and find some calculator tricks and just go through the process with this equation. Now, don't let the fifth root right here throw you off, the fact that I've written it this way right here. This is the real number right here that I'm taking the fifth root of. So when I rewrite this rectangular form of this complex number into polar form, I want to be thinking about the 1 and ignore the fifth root for just a moment. So let me graph that. It'll be really easy to change this to to trig form based on the graph, because the real part is 1 and the imaginary part is 0. So I'm not going anywhere in the vertical direction. I'm going 1 in the horizontal direction, in the real direction. So I get this vector right here representing the complex number 1. Obviously, my r value is 1 since that's the length of the vector. And theta is going to be 0 here, 0 degrees, because I haven't rotated at all. So I can write this. I'm going to go ahead and write the understood 1, CIS 0 degrees. Rewriting that in polar form. I haven't taken a root yet. I've just rewritten it in polar form. Now we're ready to find the root, and I need an r value. The r value for the roots come from taking the fifth root of the r value that you started with, and so that's just going to be 1. Now I also need a theta statement, and that's going to be 0 degrees plus every coterminal angle, so 360 degrees times k. Since I'm taking the fifth root, I want to divide each of those terms by 5 to get an expression for each of my solution angles. 0 degrees divided by 5 is still 0 degrees, and 360 divided by 5 is 72 degrees. And then that is multiplied by k, where k is going to be 0, and then 1, and then 2, and then 3, and then 4. That will give me 5 solutions. Or find your first angle where k is 0, and I get my r value of 1 CIS 0 degrees. And then my next angle is just going to increase by 72 degrees. So 1 CIS 72 degrees, and then 1 CIS 144 degrees, 72 plus 72, and then 1 CIS 216 degrees, I think that's right, and then 1 CIS 288 degrees. There's just a difference of 72 degrees between each of those angles. Now those are my answers. Those are my answers in polar form, but I'm going to graph it like they tell me to graph it, and then I'm going to go ahead and convert those using the calculator to rectangular form, because you're going to be asked to do that as well. Let's go ahead and graph these in the trig form. Now since the r value is 1, really I'm graphing these vectors within a unit circle. Let's see if I can find my circle. So we'll say that this circle centered at the origin is 1 unit It's 1 unit in every direction. When I graph these on there, I'm always going to start my vector at the origin, and the first one lies right here on the x-axis. That's pretty hard to see, but it goes all the way to that circle, which represents a radius of 1. My next vector will be at 72 degrees, and I'm just going to approximate, and then 144 degrees is somewhere over here in quadrant 2, and then 216 will be down here, and then finally we have a vector that's over here. Now those are not they're not great. Probably make some adjustments to that, but you're going to be identifying these graphs from multiple choice anyway. It's pretty hard to just estimate where those are, but each of the angles is 72 degrees apart. That we start at 0, and then the next vector is at 72 degrees, and then from there to the next one is 72 degrees, because that's what we're adding every time to get to the next angle. So that's the graph of it. Now let's take a look at how we would write these answers back in rectangular form, and let me give you a calculator trick for doing that, because it's a lot of typing unless you use your calculator's ability to store values and everything. Instead of, well, the first thing you want to do is probably type in the equation RCIS theta, but you can't abbreviate it. As far as I know, in your calculator, that's not going to work. So you have to use the multiplication after the R. You can't just do R parentheses, because it will think you're talking about a function. So type R times parentheses, and then you're going to have to go and type in the cosine, and let's use A for angle or any letter that you want, and then plus I, and it has to be the I from the pi button. It can't be the letter I, and then times sine of that same letter A. And right now you can see that the R and the A are not in bold, so I have a cast, so it gives me this answer right here. Your calculator may give you something else. It doesn't matter what it tells you that is. You don't have anything stored for R and A yet, so it's not really evaluating anything. I just need to get that expression in there. Now I want to store my particular R value, which is 1. I want to store that to R. And then I want to store my first theta value. So you can define that instead of storing it if you want to. It doesn't matter the order that you do this. So A is defined as 0, and my calculator is in degrees. So now I've got those values substituted or stored in my calculator. I can go up here and highlight that expression and press enter. Notice that before I pressed enter, the R and the A were in bold. That means that those are actual variables that the calculator knows, that has numbers to substitute in for. So it substitutes them in, and I get that real solution 1 that I knew from the very beginning was going to be one of the solutions. My R value is not going to change in this problem, but now to get the next answer, all I have to do is assign the next value, the next angle of 72 to A, and then go up and highlight that expression, and I don't have to retype it. Just press enter and then press enter again. Now again, I'm on the cast, and I always forget that I have to approximate here, or it gives you that weird answer. Since these are not special angles, you will have to give decimal answers in your solution. So here, I don't know if you can read that, but it would be 0.309 plus 0.951 times I, depending on what they ask you to round to. Now I want my angle value to be 144, so I can store 144 to A, and then go back up and highlight that expression. And this time I'll remember to approximate, and I get negative 0.809 plus 0.588 times I. So you get those rectangular forms right back from your calculator.